Okay, let's talk about the motion of charged particles. In the last video, we introduced what a uniform electric field actually is. And in this video, we're going to talk about how a particle will behave and how it will move if it's placed in that uniform field. So in this topic, which is essentially motion of charged particles, we'll start by looking at particles that will be moving vertically. So if you were to place a positive charge, this is my little positive charge over there. If you were to place it inside an electric field, it's going to be forced to move down due to the attraction between this negative plate and that positive charge. So it's going to be forced to move down. And we need to be able to describe how that motion will actually be able to work. So first, let's start with this following fact. The work that will be done on the positive charge, work done on a positive charge, should be equal to the gain in kinetic energy. What do I mean by this? If you're going to put a positive charge next to a negative charge, it's going to be attracted automatically, right? Like magic, essentially. And that itself gives some work to the positive charge itself. Now, the positive charge, you experience some motion, right? That kinetic energy is coming from the work that is being done on that charge by the negative charge itself, the big negative charge. In this case, the negative plate that will be over here. So you can easily say that the kinetic energy that you will be able to gain should be equivalent to the work done on that charge itself. Now, the work done on the charge can be calculated by saying VQ, right? So we already discussed that in electricity, potential is equals to the work done per unit charge. So the work done can be equal to the product of electric potential times Q. So VQ should be equal to half mv squared. Half mv squared is the equation that we use for calculating kinetic energy. Now, my goal is essentially to find the value of v, right? So it's essentially what is the velocity at that point that you find yourself being. So if I look at this, I can say 2vq divided by, so I multiply both sides by 2, divided by m should be equal to v squared. Now, essentially from that calculation, take square roots on both sides, v will be equal to the square root of 2vq divided by m. So using that, you can be able to then find velocity at a given specific point. This is important because if you look at this, right, the top plate, let's assume is 230 volts. Okay, the bottom plate, let's say it's 0 volts. You must be able to tell me what is the velocity when you're at this point over here, right? And you just go here, you plug in 230, the charge of that positive charge, and the mass itself of that positive charge, and you can be able to find the velocity at this point. But let's assume you're midway, right? You're at this specific point. You can easily see that the value of voltage will change to half of 230, right? And half of 230 is 115. So you have 115 volts, right? So you can easily see that the velocity also should change, and you can put in 115 there. And you can find velocity at every given point, provided you know the potential difference between the top plate and that specific point that you'll be looking at. So if you're given the charge, if you're given the mass, and if you're given the potential difference between two plates, you can therefore easily find the velocity of a particle in that specific point. So that's how we can describe motion. This little guy is holding up our equation, which is over here. So that's how we can describe the motion of particles within an uniform electric field. So there's another equation that you must be aware of. You can also use equations of linear motion, and we will explore that below. Okay, so Newton's second law of motion states that F is equal to ma, right? F is equal to ma, and we also know that F is equal to QE. So we can combine these two equations and say, hey, ma is equivalent to QE. So ma is equal to QE. We can make A the subject of formulae simply by dividing both sides by m. So divide here by m, and you divide here by m. So A will be equal to QE divided by m. Right? So now that you have the equation for acceleration, you can therefore use the following kinematic equation. V squared is equal to u squared plus 2as. Since you start being stationary at any point, your initial velocity is going to be 0. So v squared will be equal to 2as. V will be the square root. So v will be equal to the square root of 2as. Okay, but I've already discussed that A is actually QE over M. So we can plug in A over here, and we can get 2QES divided by M. Okay, but we can relate electric fields to potential difference. We know that E is equals to V over D. We've talked about this equation, guys, that E is equals to V over D. So V over D, you can replace that with E, and you know that D and S are the same thing. The distance that you have moved is the same as the distance where you have that potential difference. So the two can cancel out. So you'll be left with V squared is equals to 2QV over M, square roots on both sides. So V will be equal to the square root of 2QV divided by M. So essentially, that's what we can use. So it's a little way in which you can be able to calculate the velocity at any given point that you're interested in. So for our first video, motion of charged particles, this is how you can describe it, right? You can look at the motion of a particle vertically as it moves down in a uniform electric field. And questions will ask you a lot of things around this calculation, so you must be very mindful of that. But I hope this video was helpful in helping you better understand how this concept can be worked out.